Now let's start looking at some of our binary operators. We'll begin with union. Now union has a constraint that its two input relations have to have a property. They must be union compatible. That means they have the same number of fields, and the fields that are in corresponding positions in the two tables have to have the same type. So the first column of the first table is to be the same as the first column of the second table in terms of type, and so on. Now they don't have to have the same names, just the same types. In SQL, the expression is union, all right, and so it's quite similar to the relational algebra in that case. But in relational algebra, we write it in set notation with the big U like this. And so given an S1 and an S2 that are sets that kind of look like the red and blue balls on the lower left, their union is all the things that are in S1, all the things that are in S2, and all the things that are in both, and of course one copy of each. Now in SQL, we also had this notion of union all that you might recall. That's like union, but it doesn't remove duplicates. And in practice, people might want one or the other, depending on their performance needs and depending on the semantics they desire. Okay, so just going through an example, here's relational instance S1, relational instance S2. So it's two copies, if you will, of the Sailors table, two different instances of the Sailors table. And when we union them together, you'll see that we have Rusty twice, we have Lubber twice. Okay, but in the output, we're going to see each of them only once because we're in the relational algebra, we're always removing duplicates. Okay, next operator to look at is set difference. Like with union, both input relations have to be compatible. Their columns have to be in the same order with the same types. The SQL equivalent to set difference is except. We just write it as the minus sign here in the algebra. And if you look at our little schematic, S1 minus S2 looks like this moon-shaped thing. It's all the things that are in S1 except for those things that overlap with S2. Now for set difference, do we have to do duplicate elimination? And the answer is no, just like with selection. S1 already has no duplicates. The subtraction of S2 only removes tuples, and so S1 certainly has no duplicates afterwards. No duplicates are generated. So we don't have to do duplicate elimination after set difference. Now in SQL, remember there is except and there is except all, and I'll refer you back to the SQL slides for the semantics of except all, but let's look here at an example of set difference. We've got, again, two instances of the Sailors table, S1 and S2. And S1 minus S2 is all the things in S1 that don't have a match in S2. Well, Dustin doesn't have a match in S2, Lubber does, and Rusty does. So the answer, I would think, is just Dustin. Yes, indeed. S2 minus S1, doing it the other way around, is something else. It's Yuppie and Guppy. All right, so notice that set difference is not commutative. It's different depending on the order you do it in. So that's a very important thing to keep in mind. Union and intersection, by contrast, were commutative. And now cross product. You know it from SQL. R1 cross S1 is having each row of R1 paired with each row of S1. So if you look at the picture on the left, the cross product is this larger table on the right. And keep in mind that cross product kind of blows up the output. So the number of rows in the result is the number of rows in R1 times the number of rows in R2. Recall the term cardinality. Those bars around the relation instance names are expressing cardinality, which means the number of distinct rows. Now, do R1 and S1 have to be schema compatible? No, they don't, because we're going to concatenate their schemas, right? The type of the output of a cross product is the concatenation of the schemas of the inputs. They don't have to be the same. We're just going to stick them side by side. And in terms of duplicates, there's no duplicate elimination required because none are generated. R1 has no duplicates, S1 has no duplicates, and therefore their cross product, their combinations, are all unique. Now, we didn't look at the renaming operator row because it's not really very interesting, but it's useful in certain cases, so let's have it. It's an operator that works entirely at the schema level. It doesn't do anything to the data. It just returns the same data it gets in when it returns it outwards. But it changes the schema by renaming relations and or attributes. Note that the relational algebra doesn't actually require names. We could refer to everything in terms of positions, like column 1, column 2, column 3. And there are people who write relational algebra that way, but in our class, names are so much easier to deal with. We'll assume we're working with names, and we'll use the renaming operator as needed. So here's how the renaming operator works. It's a little row, and it takes as arguments. Its second argument is the input expression or input relation. So in this case, that's R1 cross S1. And its first argument is a schema change definition. So it tells you what the name of the output relation should be, in this case temp1, and it gives you a list of name changes for each of the positions in the output. So here it's saying column 1, I want to call that SID 1. And column 4, let's call that SID 2. Okay, so that's what this expression is saying. And the output, therefore, is a table called temp1, where the first column's SID1 and the fourth column's SID2, and the remaining columns are exactly as they were in the input. So that's it. We're actually done with all the operators in the relational algebra. All that remains is to talk about the compound operators, which are really just macros over the operators we've already learned. Here's our first compound operator, intersection. Like with union and set difference, both the input relations must be compatible. The SQL expression for this is intersect. We will write it in relational algebra using the intersect symbol, which you're probably familiar with. And as you can see in the schematic, it's those tuples that are in both S1 and S2. Let's look at an example of intersection. We have our two instances, S1 and S2. And the tuples that overlap that appear in both of them are Lubber and Rusty. And so that's our output. Now we said it's a compound operator, intersection. So what is it? How do we define it in terms of the basic relational operators that we've seen before? Well, let's work through this pictorially with our Venn diagrams and see if we can figure this out. It's going to be S1 minus something. Here's a picture of the intersection on the left. We're saying it's equal to S1, which is the full circle, minus that moon-shaped thing on the left. We've seen a moon-shaped shape before in our previous descriptions of operators. How did we get that? That's S1 minus S2. So the whole expression S1 intersect S2 is S1 minus S1 minus S2, or a full circle minus a moon, and that gives you the intersection.